Okay, so we are at page 96. Now we come back to the deterministic case. Okay, so let's take a look at one example. The example is example 4.1. Assume that we have signal S of n equal to A for some known label A. Then from equation 4.3, which is this equation, uh, if you just substitute A into this S, then you get T of X equal to A summation X of N. Then an equivalent detector divides T of X by NA to decide H1 if T prime of X equal to 1 over NA T of X. That will be uh, 1 over N because this A cancels this A, okay? But N stays. So this will become the mean of the sample, right? Mean of the samples. We're actually taking average on the samples. Then the reason we can do that to divide this NA is because N and A are all known, right? They are all known constants. So when you are comparing one thing with the other, you divide it by known constants. That is something equivalent. This is very important. If you divide something that is unknown or uh, you divide things that are very strange, it may change the unequal sign here. But the point for doing this is that they are known and constants. So when we divide it, it does not change the unequal sign. It makes the mathematics still equivalent. That's the point. But the point is it also simplifies the t of x. So we call it a new function t prime x. And then we divide it and 1 over n, but let a cancels out this a. And then we have a sample average larger than gamma prime. So, I'm sorry, gamma double prime. And so that gamma double prime will make it equal to this. And again, this is what? This is just a change of the notation. It has no physical meanings, and it has not something deep. It's not like something very deep. No, it's not. It's just a change of it's just a change of the notation. Okay, so um so we change gamma prime divided by NA to gamma double prime just to make the notation simple. But this is just a sample mean detector, right? So the sample mean detector will be like this. But the point that we are doing this is that uh, it's a sample mean detector, but however, it comes from this t, this t here. But that t comes from where? It comes from Neyman-Pearson criteria. So what we are saying here is if your signal is just a very simple signal, just like a constant A, then what happens is you do the sample mean. That's trivial. Intuitively, that's trivial. But at the same time, it by coincidence, that sample mean detector is consistent with likelihood ratio detector and it's consistent with Neyman-Pearson detector. So it's a coincidence, but that also uh, sort of demonstrate uh, the power, the power, the effectiveness of our derivation. So our derivation is consistent with our intuition. That's what well, why that's what this example is trying to demonstrate. Okay, so um, its performance is also uh, been described there. But note that if A is not smaller than 0, then the inequality reverses and we decide H1 if X bar smaller than gamma prime. Okay, so I think that's trivial, right? If you have A as negative, when you divide this, you should change the sign to smaller than, rather than larger than. It will be smaller than. So it will be, the inequality will reverse if we decide H1 uh, if X bar smaller than gamma double prime. Okay, then we come to the next example. Uh, this example is the damped, damped exponential in white Gaussian noise. So now, if let's just assume that xn is equal to r to the n for 0 smaller than r smaller than 1. What that means is you're going to see a signal that is getting smaller and smaller uh, with respect to time, meaning that we are getting something smaller with the progress of the time. It will be smaller because of the r to the n, and of course then r has to be smaller than 1. If r is larger than 1, then we get something exponential increase, which is not good. So here we will assume r smaller than 1. Okay, so from 4.3, the test statistic is what? 4.3 here. We have to multiply the sample with the signal and then do the summation. So we multiply the sample with the signal and then do the summation. And we have to assign their time index n to the n. Except here, n it happens to be the exponent of the r here. All right. So now we are at page 97. So if we take a look at this test statistic, it will be seem to weight the earlier sample more heavily than the later ones. So, right, if these are, for example, 0.8, it will be 0.8 at the first sample, and then it will be 0.8 squared, which is 0.64 to, to the second sample, and then so on and so forth, it's getting smaller and smaller. So it will weigh more heavily than the later ones. And this is due to the fact that the signal is decaying as n increases while the noise power remains constant. The signal to noise ratio for the n sample is S square n to sigma square, right? Because if we recall the signal here, it has variance sigma square, but it does not relate to n, right? I mean, for whatever n, its noise variance is always sigma square, so it does not change. The noise variance does not change, which is always sigma square. So by saying that we just write out what happens here. We will have r to the 2n over sigma squared, which will decreases with n. The detection performance can be easily determined as described in 4.3, which we will talk about later. Okay, so in general, the test statistic of 4.3 weighs the data samples according to the value of the signal. More weight is reserved for the larger signal samples. Even negative samples are weighted in the same manner because by multiplying this by this, negative samples yield a positive contribution to the sum. So the detector, the, uh, I want you to pay special attention to this sentence. The detector of 4.3, which is this one, is referred to as a correlator or a replica correlator, since we correlate the received data with a replica of the signal. So, just to recall one more time, we are actually multiplying the x, which is a sample, with the known signal, So, uh, if you recall the discrete version of the correlation, this is in fact the discrete version of the correlation. We are correlating samples with the known signals. Okay, exactly. This is exactly the form of the correlation. If you just recall, uh, in previous undergrad classes, when we were talking about correlations. This is exactly the mathematical form for correlation. Okay, so we will call it a correlator, a replica correlator. Since we correlate the received signal with the replica of the signal, the detector is shown in figure 4.1, which we will see. We'll take a look at it. An alternative interpretation of test statistics is based on relating the correlation process to the effect of a finite impulse response filter on the data. So another interpretation is, I'm not sure if you have taken the course for filter design or you have the concept of the filter. We are actually passing the data through uh, a filter while S serves as the impulse response of the filter. I think uh, if you take the signaling systems, but I believe you you might get a sense of this. I think that yeah, that course you might have learned about this because I teach that classes in my last semester, signaling systems. So finite impulse response filter. So if xn is input to a filter with response h, then it will serve as uh, in fact it will serve as a something that similar to correlation. Okay, so let's just put it aside for a second and use the concept of correlator. Let's think about this. We have x that comes in, and then we have s that comes in, and you multiplied it, both of them, and then you put it into a summation, you get t, then you compare with the gamma prime. If the gamma prime is if it's larger, then we will say h1. If gamma prime is smaller than gamma prime, then we say H0. That's a very ordinary form, right? This thing is very ordinary. It's just ordinary implements this function. Then the other thing is a bit abstract. This is a correlator. And the other thing is, if we have x of n, it comes to a h, uh, and then we have to be very careful about this h because we need to set h as a time reversed version. Remember that it's a time reversed version of the signal. Then it will be Hn needs to be Sn minus 1 minus small n, capital N minus 1 minus small n. If you put the impulse response like this and you put it here, and then that when that Xn comes in, you sample it at time equal to n minus 1. You get exactly this thing. Okay, this can actually be carefully derived. If you recall what we say about impulse response and filter in signals and systems, and then you set that H to be a time reversed version, and you just try to derive the output when it passes through a filter. The data X actually have to be convolved. Recall the word convolution. It's a convolution operation. You convolve that X with this H, and you carefully derive, because it's a complicated summation thing, right? You do a lot of summations and convolution. So you convolve it, and then you take the sample at small n equal to n minus 1, you get exactly just this. You get exactly this, but only at n minus 1. If you take it at a different time instant, you get different values. So this is a sort of a filter version of it. Filter version. So once you get this t, then things at the later part, that is simple. That is just like this. So you compare it with gamma prime, or if it's larger, then you get h1. If it's smaller, then you get h0. Okay. So let's take a very careful look at this. We put the data into a filter, and then we design the filter to be a time reverse version of the signal. And since that signal is known, then we have no problem with the impulse response Hn. Right? Okay. Then we come to page 98. So for this n equal to 0, 1, all the way to n minus 1, the output at time n is like this. This is just the output at time n for the convolution operation. Recall this. It's the output of the convolution. Okay, so once we have this output for convolution, if we let the impulse response be a flip around version of the signal, which is just what I say, it's a time reverse version of flip around, whatever way you like to say it. You get this h equal to this. This is artificial, all right? Okay, here I have to emphasize this is artificial because we can design it. So it's under our control. We just set it this way. Then yn will be equal to something like this because you just put this into here. Of course, the index has to correspond to each other. You correspond it and then you set it properly. You get something like this. You get something like this. And then now the output of the filter at time n equal to n minus 1, then it will be something like this. Right? Here we are talking about the output of the convolution and then set it this way and then look at it at n minus 1 and we get exactly this, which is exactly the same as 4.3. Okay, so now we have successfully derived the output, and then we also sort of prove what happens at the output at time equal to n minus 1. That is exactly the test statistic that we like to have. Right? So with the change of the summation variable, so on and so forth. So this implementation of the NP detector is shown in figure 1b. So we just describe it. It's known as the match filter. Match filter. So you can think of the match filter as just a name of the filter, or you try to understand what we mean by match filter. The filter impulse response is matched to the signal. In other words, the impulse response H is designed to be a flip around version or time reversed version of the signal. So we say that the impulse response is matched to the signal. So we call it match filter. Okay, so the match filter impulse response is obtained by flipping s about n equal to the 0 and shifting to the right by n minus 1 samples. So this is a physical interpretation. And of course, its mathematical form is here. Is here. Okay, so we will this we'll just skip some of the uh, discussions for the frequency domain. We would rather emphasize on more on the uh, on the detection and time domain. Okay, so the match filter will be something like this. Let's say if you have a s equal to this, then the match filter h of n will be something like this. You flip it around and shift it, so it looks like this. You flip it around and shift it, it looks like this. So this h corresponds to this s. This h corresponds to this. It's just an example, just an example. Okay, I think we'll take a break for a couple minutes, then come back later.